Okay, just really quickly, please. I would like you to take out your 6.1 notes. Sorry, it says 6.1 to 6.2. It's both sections in that notes package, so 6.1 to 6.2. And I just want to do one last question because I want to try and piece everything together. So let's take a look at this. A solution has a what? What the hell is this? What is square brackets OH minus mean? Hydroxide concentration. So you have a hydroxide concentration of 9.31 times 10 to the negative 10 moles per liter. What I want to know is this a really large concentration or a really small concentration?
Small.
It's pretty small, isn't it? Right? So this is a very tiny concentration. So what does that mean, Idris? If this is a really tiny concentration of hydroxide, what does that mean about our hydronium? Do we have lots of it or not a lot of it? What's the relationship between hydroxide and hydronium? If I take a look at my picture here. When I have lots and lots and lots of hydronium, what do I have of hydroxide? Very little. So if I have very large amounts of hydroxide, I have very little hydronium. Here, in our example, if we have a very tiny amount of hydroxide, what does that mean about our hydronium? There's lots of it. So what do you think? Let's just take a guess. Do you think this solution is going to be acidic or basic? I don't know. Wim, what do you think? Basic. Okay. So let's just keep that in the back of our minds. Okay. We should be able to kind of understand this question a little bit, and then be able to run through the math and double check and see if our math works out correctly. How can I get the hydronium? This question is asking me for the hydronium concentration of this particular solution. How is that possible for me to get hydronium concentration? What can give us a hydronium concentration? Do you know what things can give us a hydronium concentration, Wim? Okay, so what could we get from this information here? What could we get from this information here? The POH, right? So this could give you POH, the power of the hydroxide, right? So we can get POH. Well, from POH, where can you go with that? pH. Oh. If we have pH, can we get hydronium from pH? Absolutely we can. So that's what we want to do. If we go back to the previous slide, if I want to get hydronium, the only way to do that is from the pH. So if I want to go from hydroxide to hydronium, I got to go from hydroxide to POH, from POH to pH, all the way up to hydronium. So I'm going to have to do 3 separate calculations in order to get there. It won't be that bad. They're pretty quick calculations. It's not that bad. I want you to just take a second and think about this. Okay? What is the approximate POH of this concentration? Jenna, what is it? It's 10, right? Approximately. I'm not saying it is 10. I'm saying it's in the order of 10. Okay? So if our POH is 10, what's our pH? Does that make sense? Our pH is going to be 4? Yeah? So if our pH is 4, is this acidic or basic?
Acidic.
It's acidic. Does that make sense? Okay, so anyways, let's go through this and let's actually do this. How many people completed the homework from 2 days ago? No? Nobody finished the homework from 2 days ago? Nobody memorized those formulas? That's the second time I've got you with the same thing. Really? Come on, you gotta be quicker than that. Okay, have you memorized those formulas? Remember, there's only 3 formulas that you have to memorize. Okay? Without looking back at it, let's see if you can remember. Yes, so don't look at it, okay? pH is equal to what? Right? Acid, right? pH, power of hydronium, so you need a hydronium. Okay, instead, how could we go backwards? Instead of doing that, okay, how could I get hydronium? 10 to the negative pH, right? Because pH, what does pH stand for? The power, the exponent on the hydrogen, right? The power of the hydrogen. Okay, and then what's the last itty bitty tiny little calculation that you need to know? Right? Why is it that I said that there's only 3 calculations you have to memorize when there's really 5? So what's the other version, Wim? Okay, so instead of saying pH, I could say what? Yeah, POH is just negative log of the hydroxide. Remember, that's the exact same thing as that, right? It's the exact same thing, so you don't really have to memorize. If you have to memorize 2 separate equations, go ahead and do that. Okay, if that's what you have to do, then go ahead and do that. Okay, instead of hydronium concentration, what else could I do? Concentration of what? Hydroxide is equal to what? 10 to the negative POH. Do you see how POH and OH always go together? Right? POH and OH always go together, and pH and hydronium always go together? Yeah, that's okay. Alright. So if you have to, this is the 3rd day in a row that I've told you you have to memorize these equations. You have to memorize these equations. You have to put in the work and actually memorize them. Because if you ask me on a quiz or a test or something like that, P.S. we're going to have a quiz next Tuesday. I'm not looking at the calendar, I'm just doing mental math in my head. Yeah, we're going to have a quiz on next Tuesday. And if you ask me on the quiz, you say, sorry, Mr. Walton, I didn't memorize the formulas. I'm going to be like, okay, all right, good talk, whatever. So we want to go from hydroxide to hydronium. What can hydroxide give us? What's the only thing hydroxide can give us? POH, right? POH, that's terrible, but whatever, you know what I mean. POH is negative log of the hydroxide. So it's negative log of 9, whoa, that's the worst 9 in the world, 9.131 times 10 to the negative 10 moles per liter. Again, this is going to be really close to 10, but it's not going to be 10. It's going to be 9 point something, right? Yeah, what is it? 9.031. 05. Does anybody disagree with that? No? Okay, good. Blah, 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 blah. What are the units on this thing? No units. pH and POH don't have any units. Good. Hey, are we done the question? No, then don't round it yet. Okay. So that's the POH. So where can you go from there? You don't want to go back to hydroxide because that's useless. Where can you go from POH? pH. So I'm not even going to write it down. I'm just going to go 14 minus this. 14 minus this. 4.9689 blah, 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 blah. So, yes, indeed, this absolutely is an acidic solution. 100%, totally. Are we done the question yet? No, then you can't round it yet. Where can we go from pH? What's the only other thing we got to do? How do we get hydronium concentration? 10 to the negative pH, right? So 10 to the negative 4.96894, blah, 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 blah. So when you put this into your calculator, hopefully you get, like, I don't know, 1.01 times 10 to the negative 5. Something like that. What is it? 1.07? Sure. 1.07 times 10 to the negative 5 moles per liter of hydronium. Now let's go back to our original information, way back to the beginning. How many significant digits are in my original information?
3.
Is it a pH or a POH? No, then it's normal rules, right? Is it a pH or a POH? No, then we think about our normal significant digit rules. I see 3 numbers, so we need 3 numbers in here. Okay? Now my final answer is my final answer a pH or a POH? No, so then it's just the normal significant digits. 1.07, 3 digits, right? Times 10 to the negative 5. How difficult was that question? Okay, how difficult is it going to be if you haven't memorized the formulas? It's going to be impossible, right? There's no way for you to solve that. There's 0 way for you to solve that. So I just wanted to make sure we were all on the same page. I'm going to give you an assignment later, and I'm going to ask you to finish that assignment for Monday. But we are going to move on. We're going to mosey on to something else. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. How do I put that? I didn't. I asked somebody, and that's what they told me. Okay. So let's go. I don't know how to do it on your calculator. Let's figure it out. We need to go 10. Okay. We need to go 10 raised to the power of 5 to the x. Raised to the power of 5. So you get 5 and then go 4.9689. But it's negative. Yeah. Perfect. Equals. Perfect. And that is 1.07. EXP is times 10 to the power. Yeah, that's our E. Okay. So your EXP is that. If I wanted to put this in my calculator, I would go 1.07. 1.07 times 10 to the power of negative 5. That's your scientific notation. Okay. Yesterday we were talking about indicators. Do you need one more? 2. You need 2 more. Wow. I handed out 7. Okay, all right. Okay. We're going to start something new. I want to take about, I don't know, half an hour, 40 minutes to do this, and then we're going to move on to something else. Or then I'm going to give you an assignment. Indicators are substances. They are chemicals that change color based on the pH of the solution. And do you remember seeing that yesterday? In the lab yesterday? Yes, hopefully you do remember that. I can't pull it up. I just don't have it prepared, so I can't pull it up. Okay, for example, litmus. Litmus is an indicator that's pulled off of like this lichen-y substance. Do you know what lichen is? Yeah, it's almost like moss, right? And it grows on stones and trees and stuff like that. And its lichen has a symbiotic relationship with lots of other organisms. So lichen, we can basically take lichen, this organism, this microorganism, and we can get this chemical called litmus. Now litmus changes color based on pH. What is litmus when it's acidic? Red. What is litmus in basic conditions? Blue. And I don't know if you can tell, but it's kind of this weird purpley color in the middle. It's supposed to be. But often, neutral substances just don't change the color of litmus. Is that okay? So basically what litmus paper is if you took a sheet of paper, if you took any regular sheet of paper, and you dipped it into litmus, and then you dried it, you would get litmus paper. That's all litmus paper is. And then if you want red litmus paper, what chemical do you have to spray on it before it dries if you want red litmus paper? Anything acidic. Anything acidic at all. And then if you wanted blue litmus paper, what chemical would you have to spray onto that litmus paper? Yeah, and then let it dry, and then cut it up into little tiny strips of paper and give it to students for pennies on the dollar. Okay? So indicators serve two purposes. The first purpose they serve is they are a diagnostic tool to identify the pH of a substance. If I gave you a substance, okay, if I had a beaker of some sort of a clear, colorless solution, you could do a bunch of diagnostic tests to see what the pH was on here, right? If I put litmus paper into here and it turned the litmus paper red, could you narrow down the pH of this unknown substance? Yeah. What pH are you certain it could be if litmus paper was red? Anything less than 7. 6, 6.5, 5, 4, 3, 2, 1, 0, -1. You know what I mean? Any of those values are valid, so it's a diagnostic tool to identify the pH of that substance. And also, we'll talk about this a little bit later, it can be used to indicate when a reaction is complete. So I can put an indicator inside a beaker, and the moment it starts to change color, that's when I know a certain chemical reaction might be complete. So we can use it to tell us, oh, your chemical reaction's done now. Stop doing whatever you're doing. Does that kind of make sense? Yeah, okay. We're going to focus way more on the very first one. What I want you to do is I want you to focus up on, I've got them split up. I kind of screwed up. Okay, so I've got the two halves of a certain table from your data booklet, but I split them up onto 2 different pages, so I apologize about that. This is on page 10 of your data booklet. So if we were to look at the Chemistry 2030 data booklet, page 10 is way at the back. We've got a list of a buttload of indicators on here, and we've got a list of all of the pH ranges and what colors they will turn. So let's just take a look. I want you to just anybody pick any one of these indicators. Pick one, doesn't matter.
Red.
Cresol red. Let's look at Cresol red. Perfect. Ooh, you picked a complicated one. I love it. Okay? So let's look at Cresol red. In here, the suggested abbreviations, those are like, if you wanted to write a chemical reaction and you wanted to put the indicator in that chemical reaction, we would put this. Now, the problem with that is when you see H2Cr, what two elements does it kind of look like we're talking about? Hydrogen and chromium, right? What you have to understand is that it's actually talking about Cresol red. We just use the two letters of the words to put in there for abbreviations, okay? So that's okay. Thymol blue will be TB, orange 4 will be OR, whatever, it's all good. Now, let's think about this for a second. There's two different pH ranges for Cresol red. What that means is that Cresol red can undergo two different chemical reactions, okay? When we strip away the first hydrogen from Cresol red, do you agree? When we go from H2 to H, we're stripping away a hydrogen or a proton off of this. Then all of a sudden, what kind of color do we transfer from? Red to yellow. So what that means is if we're at the pH 0 or below, right? Because you can go below pH 0, what color will it be? Red. If we're at a pH of 1 or above, what color will it be?
Yellow.
Yellow. And if we're smack dab in between these two things, what color would it be? Red and yellow, otherwise known as orange. Is that okay? Does it make sense? Because when we're in between, we've got a little bit of the red version and a little bit of the yellow version. So we've got some red and some yellow making an orange solution because you can't see them. Okay, what about Cresol red at a pH of 7? What color is it going to be?
Yellow.
Yellow. And what about at a pH of 8? What color is it going to be? Red. What about a pH of 9, 9.0? Where would it be on this range? Idris?
Why is it yellow?
What do you mean, why is it yellow?
I thought we were talking about only red and blues. What?
I don't know where you... Oh, okay. I totally... I know exactly what you're talking about. You're thinking back to litmus.
Yeah.
This is a totally different chemical now.
Okay.
We're just talking about... Okay, we talked about litmus. Litmus was red all the way to blue. And now, throw that out the window. And we're going to talk about a totally different chemical. Okay? All right. So what about at a pH of 9? What color would we be? We'd be past 8, right? So we would still be red. Does that make sense? That's, boom. All of a sudden we've learned everything basically that we need to know about indicators. Okay? So what I want us to think about is I put it in the notes. If you don't want to look at your data booklet, I put both halves of the table in your notes, but that's fine, whatever. So both halves of your table are in here. Let's go ahead and let's answer some questions. I'm going to do a couple examples with you, and then I'm going to get you to do some examples by your own. By yourselves. By your own, whatever. Okay, what I want you to do on your data booklet or in your notes, I don't know, it'll probably be easier to have your data booklet out, but look at orange 4. And I want you to try and find where 3.7 would be on the indicator orange 4.
It's yellow.
So let's look. Orange 4 is 3.7. Is it in between these two things? No. Is it lower than 1.4?
No.
Is it higher than 2.8? Yeah. So it doesn't matter. It doesn't matter how much higher than 2.8 it is. All that matters is it's higher, so it'll be yellow. Are we okay with that? Okay. Now I want you to understand 2.8, the pH 2.8, does it belong to the color yellow or does it belong to the color orange? It's stating for you that that's when the yellow color really begins to dominate. okay? So that's the beginning of yellow, and that's the beginning of red. So if you're 1.4 or lower, right, it'll be red. If you're 2.8 or higher, it'll be yellow. It's inclusive of those values, okay? Do you want me to walk you through any of these?
Sure.
Yeah.
Okay, orange 4 was red with a blue marker, whatever, that's fine. Let's look at methyl orange. Methyl orange, 3.7, right? So where's 3.7? It's in between, so Wim, what color will it be?
Yeah, orange 4 is.
Oh, it's yellow, sorry. So orange 4 should have been yellow, sorry. Methyl orange, right? 3.7 is in between, so it'll be the combination, which is orange. Perfect. So it'll be yellow, and then this will be orange. Okay, let's look at bromo-cresol green. Bromo-cresol green, what color will it be? It'll be yellow. We're lower than this section, right? So it'll be yellow. And then thymol blue. Where is thymol blue? We have at the top, right? Okay. So thymol blue, 3.7. Where is that? Right? It's past the first range, but it's before the second range, so it's yellow, right? Yeah. Perfect. I would like you to do the other ones for me, please. And I just want to ask you, can we all pronounce this second indicator all at the same time? Phenolphthalein. Say it with me for it. Okay, ready? 1, 2, 3. Phenolphthalein. Perfect. There's the dreaded F sound right into a TH.
There's like 4 months in it.
Phthalene. Phenolphthalein. If you want to call it phenolphthalein, that's fine, but it should be phenolphthalein. So go ahead and do those other 4 for me, please. Boom, boom, boom. I'll give you 30 seconds. Indigo carmine. Do you know what? You've seen indigo carmine before? Yeah, you've seen it. That's the color of jeans. Phenolphthalein. Yeah.
You do have to start. Yeah. I didn't see the red, so I just thought they were like.
Okay, so that should have been enough time to try these out. So we're looking for 9.1 and phenol red. Where is phenol red? Perfect. So 9.1 will be red. Good. Then we look 9.1 for phenolphthalein. Where's 9.1? In between colorless and pink. So what would be in between colorless and pink? Light pink. Pale pink. Salmon. We're not going to use salmon. So this is going to be red. This is going to be a nice, oh yeah, it's going to be a nice pale pink color. Thymolphthalein. What about thymolphthalein? It's going to be less than 9.4, right? So it'll be colorless. Thymolphthalein is colorless. And then thymol blue. Thymol blue, where's 9.1? It's in between these 2 ranges, so it'll be green, right? Yep. Good. And then the very last one, what color would indigo carmine turn in pH 12.2? Not brown. Indigo, carmine, and 12.2, what would it be? Green, right? It's in between 11.4 and 13, so it's green. Okay. Holy. So now what I want to talk about is I want to talk about slowly adding one chemical to another. And so let's talk about slowly adding one chemical to another. Indicators will change color based on the addition of acids or bases to a solution. So let's think about this. Pick any one indicator from that list and let's talk about it.
1, 3, 5.
Oh my god, don't take the one at the very bottom. Okay.
Alizarin yellow.
Alizarin yellow. Let's talk about alizarin yellow. Okay, because we used alizarin yellow yesterday. So what's the pH range for alizarin yellow? 10.1 to what? 12.0. So let's think about this. If it's 10.1 or less, what pH will it, or what color will it be? It'll be yellow. So what I want to say is that anything less than this will be yellow all the way up until here. Anything more than 12 will be what color? Red. And that's including 12 or higher, right? So what's going to be in the middle? What's 12.2 to 11.9? It's going to be orange, right? So let's think about this. Can you just wait for 30 seconds? Yeah. So what do you want to start with? Do you want to start with something really, really, really acidic, or do you want to start with something really, really, really basic? Okay, let's say we had something really, really, really acidic. So let's say we had a solution. Let's say we had, no, you know what? Not yet. Let's say we had a hydronium concentration of 1 times 10 to the negative 2 moles per liter. What color would this solution be if you put alizarin yellow?
No, that would be a base.
I don't know. You tell me. Let's think about this. What value can you get from hydronium? You can get pH. So Luke, tell me the approximate pH of this solution. It's 2. So it will be yellow. Will it be yellow? Right? All the way, if we look at our pH spectrum, 0 is way down here and negative 1 is way over here, you know what I mean? Okay, so we're right here. Boom. A pH of 2. Now, what I'm going to do is I'm slowly, drop by drop, I'm going to add a base to this, okay? So I'm going to add a really super concentrated base. What does base mean? What chemical do you know is inside every base? Hydroxide, right? Okay? So what's going to happen? As I add this base, what's going to happen to my pH? Drop by drop, it's going to incrementally move up this line. Would you agree with that? Drop by drop, it's going to move up and up and up. And so what color transitions are we going to see? We're going to go up and up and up and up and up and up and up. And then finally, let's say our pH, we're going to end at a pH of 13 or something like that. So what color in my beaker, what physical colors will I see at the beginning? I'll see yellow, and then I'll add a drop, and 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 what color will I eventually get to? Orange. And then I keep going, and then I'll eventually see red. Does that make sense? So if I slowly add the base, I'll see that transition. What would happen if I took an entire bottle of the sodium hydroxide, and instead of adding it slowly, I just dumped the whole bottle in right away? What color change would I see? I would go straight from yellow, and because it's a really drastic quick color change, I'd go straight from yellow, straight to red. You would not see hardly any orange in there. Does that make sense? Okay, so that's the idea behind these color changes. So let's think about what color changes would occur in a solution of bromothymol blue if it started in an acidic solution and we slowly raised the pH by adding a strong base. The key word here is slowly adding it. What color transition would I see? I would start by seeing a yellow. Oh man, that's hard to look at. Okay, all right. And then what would it turn into? And then I would see green. And then what would it turn into? Blue. And then I would see blue, right? Good. So when I look at that, I look at bromothymol blue, bromothymol blue. So we start out in an acidic solution, it's yellow, and then we slowly transition into the green, and then we slowly transition into the blue. Perfect, no problem. Are we kind of okay with this? Is that pretty straightforward? Yeah. The next one's a little bit trickier. Do you want to try it, or do you want me to walk you through it? Okay, let's walk us through it. What did we need to know? What kind of stuff do we need to know for where we're starting with? What type of value do we need in order to really start by picking a color? We need a pH, right? So that's our goal, is if it gives you a pH, then that's awesome. But if it doesn't give you a pH, you got to somehow try and find a pH, okay? Does it give us a pH? No. Well, what do? We give up. Give up. School's up. Nah, go home. Whatever. We're done. What do we have in here? 0.1 mole per liter what? Sodium hydroxide. Now bear with me for a second. Okay, because we're gonna have to steal some ideas from our previous unit. What's the formula for sodium hydroxide? NaOH. And when sodium hydroxide dissociates, how many NAs and how many OHs are we going to get? One sodium ion and one hydroxide ion. Now, don't freak out if you have 0.10 mole per liter of this thing. What's the concentration of hydroxide ions? The exact same concentration, right? Yeah. We're okay with that? Woo! Okay, awesome. We found our hydroxide concentration. Our hydroxide concentration is this, okay? Now, where can you go with hydroxide concentration? How can we want a roadmap to get us to pH. Wim, what can we do? So if this is our hydroxide concentration, right? We can go from that to POH, and as soon as we get from POH, then we can go to pH. So somebody tell me what the POH of this hydroxide is. Are we okay with that? Nope. How do you get POH from a hydroxide concentration? POH is negative log of the hydroxide concentration, right? So if you go negative log of 0.1, you will get 1. So if my POH is 1, what's my pH? 13. So what color will methyl orange be in a pH of 13? It will be yellow. It will be big time yellow, right? Okay. So what are we slowly adding to this thing? Base. So we're going from yellow to what color? Orange to red. Does that make sense? That's all we're doing. We're just going from yellow to orange to red. So our transition would be yellow to orange to red. Whew! What color change would occur if we slowly added a strong acid to this thing? Oh, sorry. We answered both questions at once, right?
Yeah.
Sorry, that's my fault. What color would it be? It would be yellow, right? And then we think, what color would it slowly be if we added a strong? Yeah, blah, 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 blah. Okay. Can I get you to do some questions? Is that okay? Yeah? Again, remember, sodium hydroxide, well, the concentration of hydroxide is that concentration, right? So the concentration of sodium hydroxide is the concentration of hydroxide. So what color, if this is a POH of 1, then it's a pH of 13. What color would that be? And what color would we, if we slowly add a strong acid? Go ahead, do those two questions for me, please.
It's not as fat anymore. Just like what to do the eyes. You're gonna be reading this one. Okay. I'm gonna put mine. I don't split. Two boys then. Because they're on the island with no parents and they start to realize there's they kill Simon. They kill the whole kid. And then Piggy dies when someone throws it away. No, because they're also planting grapes. So they're killing still and they think Simon is
Okay. Bromocresol green. What color is it going to be in a POH of 1? So in a POH of 1, we have a pH of 13. So let's look at bromocresol green. So if it's got a pH of 13, what color is it? Blue, big time blue, right? And if we slowly add acid, it's going to go blue to green to yellow. So it's going to start out blue, and it's going to go blue to green to yellow. Perfect. If you have alizarin yellow in this solution, remember, if alizarin yellow in a 0.1 mole per liter solution of sodium hydroxide, right? So this much hydroxide is a POH of 1, which means it's a pH of 13. So what color are we going to start out as? We're going to start out as red, right? And it's going to go more orange, and then it's going to go yellow. So red, and then it goes red, orange, yellow. And we saw that yesterday. We kind of saw that yesterday. We hopefully saw that yesterday when we were looking at our results. I want you, this is, again, I am not a good photographer, but this alizarin yellow, right? It's yellow, 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 yellow. Then finally at pH of 11 and 12, it starts to turn orange. That's the idea, okay? Especially pH 12 is like, this is a very loose pH of 12. It's not really pH 12, but it's very close. So this should be quite orange, and that's exactly what we see here. So alizarin yellow R. It should be closer to orange in those really high pHs. And so hopefully that's what we saw yesterday. This part is probably the hardest part. Everything else has been pretty easy so far, so I just want to this should take 10 minutes, but I want us to really focus on the process. Is that okay? Let's really focus on the process of what we're doing. Now, the way we handle this, basically what's going to happen is it's going to give us 3 different indicators, or 2 or 3 different indicators, and it's going to tell us, oh, it was this color in this solution, or in this indicator, but it was this color in this indicator. And what that'll say is that'll say, oh, well, your pH can't be less than this and it can't be greater than this. So you'll have a very definite pH range that your solution has to be in between. So the way that's best to do this is to just kind of create a chart. And what we want to do is we want to say, okay, for every indicator, we're going to write the letters pH. And what we want to do is we want to say the pH either has to be greater than something or it has to be less than something. Okay? And then we'll pick the highest of the low ranges and the lowest of the high ranges, and that'll pinpoint what pH range we have to be in between. Now, I know that that's confusing at first, okay? But let's try this out. I don't know what's going on over there. Can you hear them? Yeah. I don't know what's going on. Okay. A solution has turned yellow when we added methyl orange to it. So let's think about this. Let's look at the pH. And what range does it have to be in if it's yellow and methyl orange? It has to be, could it be 4.4? It could be 4.4, and what else could it be?
Higher.
Anything higher than that, right? So our range is what's the lowest pH we could possibly get from this combination? 4.4 is the lowest we could possibly get, okay? So what I'm going to say is, let's say, okay, our concentration has to be 4.4 or greater. That's our lower boundary for our pH. Do you agree it can't go any less than this, or else it wouldn't have been yellow at that for that indicator? Whew, okay. It turned red when we added methyl red to it. So let's take a look at methyl red. So what colors or what pH ranges can we be red for methyl red?
4.8.
4.8. Can we be higher than that?
No.
No. So that's an upper boundary. Does that make sense? So we can be 4.8 or anything less than 4.8. So what I would say is we're doing another indicator. So my pH has to be less than or greater than 4.8. So what's the pH range of my solution? Has to be that. Has to be in between 4.4 and 4.8.
Could you just put them on the same pH?
I could, but that would only work if you had 2 indicators, right? Because you would have one indicator on one side and one indicator on the other side. Okay. now I just want to take a second and I'll see if I can amend this a little bit. No, I can't. I can't amend it, so never mind. But we'll just do the next example here. A solution turned yellow when we added alizarin yellow R, and it turned bright pink when we added phenolphthalein, and so we could do the pH range of this. That'd be fine. So a solution turned yellow when we added alizarin yellow R. Yellow when we added alizarin yellow R. So what does that mean? So could we be a pH of 10.1?
Yes.
Yes, we could. We could totally be a pH of 10.1. What else could we be?
Or go less than.
Anything less. So what that means is we cannot be higher than 10.1. So I would say my pH has to be less than or equal to 10.1. Now let's do another indicator. A solution turned bright pink when we added it to phenolphthalein. So look at phenolphthalein.
Who invented that word?
It's a combination of two words. So phenol, and then I don't know where phthalene came from. But phenol is a very specific thing in chemistry. It's a very specific group. But okay, let's take a look at this. If it's pink, well then what could we be? We could be 10.0. Could we be any less than 10.0? No. What about any more than 10.0? So this represents our lower boundary. We cannot be lower than 10.0. So when I look at this, we cannot be lower. We have to be greater than or equal to 10.0. So what's our pH range? 10.0 to 10.1. Okay, is that okay? Now, we're going to be, can I just make up an example to really kind of drive the point home? On an assignment or on a quiz or on a test or something like that, I don't have to give you just 2 pHs or 2 indicators. I could give you 3 or 4 indicators. And so let's try this. I'm gonna take methyl orange, bromocresol green. Sorry, no, I'm gonna take methyl orange. That's good. I like this. So in the indicator and what color it is, and then you have to tell me what the pH range is. So methyl orange, and then we're gonna take methyl red, and then we're gonna take phenol red. So in methyl orange, it was yellow. In methyl red, it was yellow. And in phenol red, it was yellow. Oh, look at that. Woo! That's interesting. So I want you to try this. You and a friend or something like that. I'll give you a minute, and I want you to tell me what pH range does this have to be in. What's the highest and the lowest values? Yes, sorry.
Oh my god.
And then 6.6 for me.
And then what's the last one?
6.6
Yeah, that's fine. Yeah. pH
I got mine too.
Yeah.
Yes. Does that make sense? So you're going to have two on the lower boundary, and you take the higher of the two, because one doesn't matter. Yeah. No. Nope. Okay. Try it again.
Can we use like different signs, or we just have to use this?
You don't have to use that. Okay. And there's a pictorial way of doing this. If you don't like the signs, we can put up a pH spectrum, and then we can solve it using pictures if you want.
I don't mind the signs. It's just like, you know, there's a greater
You
and
could,
then there's a lesser.
yeah, you could state that use the words less than or greater than if you wanted to. That would be fine. Okay, what I like to do is always say that pH has to be less than 4.4. No. Nope. So pH has to be greater than 4.4, but it also has to be greater than 6.0. So one of these things is redundant. One of these things doesn't matter. Right? The 4.4 doesn't matter because we know it has to be greater than 6, and by definition it has to be 6. Does that make sense? Sorry.
Nope, that's
okay.
Less. That's
Yeah. Be less than 10.1, but greater than 10. No, the bigger value has to be towards the bigger mark of the equals. Right? So I'm saying my pH has to be less than 10.1, or 10.1 has to be greater than pH. So, nope, that's perfect. That's perfect. Yeah. So what's the actual pH range? What are we bound in between? Okay, you're taking the average of the two, right? Don't take the average. Say it could be anywhere between here and here.
so you just put it in what?
Yeah, you could do that. That would be fine.
Yes.
You can draw on like one of these
Okay.
scales.
Yeah, that's fine. Yep. Okay.
Be greater than pH.
Let's try this. When I look at this, methyl orange is yellow. So let's think about this. Does that represent a lower boundary or an upper boundary? Another way of saying that is like when I look at methyl orange, if it has to be yellow, what is it allowed to be? 4.4 or anything higher than that. So my pH has to be above 4.4, right? So my pH has to be greater than 4.4. Now I understand a couple people have brought this up to me. They're saying they're confused by why I'm saying the pH is greater than or equal to 4.4. It sounds to me like maybe in your math classes you will always put your unknown first. Maybe, I don't know.
Yeah, you did that.
Would you do that? pH is greater than 4.4. Do you not see how this is the exact same thing? The pH is greater than, because it's on the big side, right? The unknown is greater than 4.4. So it doesn't matter what side the equality is on or inequality is on, right? If I move these to opposite sides, the inequality has to move as well. Okay, so it means the same thing. But what I'm trying to do, by writing the 4.4 over here, Idris, By writing the 4.4 over here, I'm trying to tell you this is the lowest I could possibly go. That's the lowest I could go. So then let's do the next one. Methyl red has to be yellow. So if methyl red has to be yellow, then what could I be? I could be 6.0 or higher, right? Again, this represents the lowest I could possibly go, right? So your pH has to be greater than or equal to 6.0. Okay, all of a sudden, one of these things doesn't matter anymore. Would you agree? One of these things has now become totally useless information. Which one is useless now? The 4.4. If something's greater than 6, by definition, it has to be greater than 4.4, right? So the 4.4 no longer matters anymore. That's why, Aaliyah, I said, you asked, can you just put them on the same thing? Yeah, if you're only doing 2, but if you're doing more than 2 indicators, it's not going to work. Okay, the next one, phenol red is yellow. So my indicator, in order for it to be yellow, has to be 6.6 or less. That means that the highest I could possibly go is 6.6. So the highest I could possibly go is 6.6. So what's my pH range? So I could be anything in between 6.0 and 6.6, right? Inclusive of those values. I could be 6.0, I could be 6.1, 6.2, 6.3, 6.4, 6.5, 6.6. Could I be 6.7? No, because it's outside of that range. So my pH range, the pH has to be greater than 6.0 and less than 6.6, or equal to those values. Okay, I don't know, hopefully that makes sense. For those of us who are really screwed up by that, if you're trying to learn that and it's just hopeless, that's fine. I've got a pictorial way of representing it using like pictures. And we can solve it the exact same way by doing that. So what I would like to do is I would like to say I'm going to give you 2 sheets to work on. One of which is due for homework on Monday. Nope. Only 3. 2, 3, 4, 5, 6, 7, 8, 9, 10.
Everyone no. I used that. Thank you. X. And it wasn't working. Everyone has to use one and then stop.
I will tell you about that in 1 second. Okie dokie.
This one is due.
Yeah, can you tell which one of these assignments is due? Oh, yes. Good. Hey, so the one with the tables on it, the one that says Chemistry 20 pH and POH calculations, I want to be very clear. That is not due for marks. But this is amazing good practice at your pH and POH calculations. The other sheet, the one that says Chemistry 20, pH, hydronium concentration, and indicators assignment, I want you to write on the top of that sheet, it is due Monday, November 4th. So you have the whole weekend. Now the reason why it's not due tomorrow, or the reason why I'm giving you so much time, is because some of you are not here tomorrow, correct?
Yeah.
Yes. Anybody in grade 12, you're not going to be here tomorrow. So, if you're in grade 11 and you're in this class, you're still coming to class, you're still going to be working, there's going to be lots of stuff to do, but we're not covering new information. Any of the grade 12s, you are not going to be responsible for doing new information tomorrow. But you are responsible for doing this assignment and this, hopefully this practice, right? I will put the key to this practice sheet on Google Classroom. I will obviously not put the key to the assignment on Google.